So if you watched other videos on my channel, you know that I developed Sonic Lifeforms, which is a technology for interactive procedural music systems in the Unreal Engine with blueprints and metasounds. And I released an iOS app of the same name, Sonic Lifeforms, the never-ending album, using that technology. And shortly after the release of Sonic Lifeforms on the App Store, the audio department of Epic Games reached out to me and they said they think my work is really cool and it's a good way to showcase the audio capabilities of the Unreal Engine. And they invited me to New Orleans to the Unreal Fest last October, and I did a talk there about my system, about procedural music in general, and this was a great experience. First of all, I really had a blast doing that talk, and I will put the link into the description of this video. And also I got to meet so many cool people, and I was able to talk to Aaron McLeran, which is the head of audio of Epic Games. He's a really cool guy and gave me so many great insights, and so many other cool people as well. So thanks again, Epic Games, for that invitation. It was really, really great. And when I came back, I decided to try and transform my Sonic Lifeforms technology from a system that is blueprint controlled, so a blueprint remote controlling a metasound, but all of the logic is happening inside of the blueprint. And I was trying to transform that into a metasounds only system. And in the beginning, I was not sure if I could do it, because I was always under the assumption that logic is always better done in blueprints. So that's the place to do the logic, and I do the audio DSP stuff in the metasound and remote control everything from a blueprint. But I tried and I finally succeeded, and it was, now it's one big metasound construction there, and there's a lot of stuff going on. And while I was doing that, I ran into some obstacles, because doing logic and randomizer logic in metasounds is pretty different from doing that in blueprint scripting, and you have to think a little bit differently if you are working only in metasounds. And so I came across a few, let's call it hacks or workflows or solutions to problems, to challenges that I found out, and I think maybe I could share it in a video. And so this is what this video is about, and I hope this is useful for some of you. So here we are in the top layer of the Sonic Lifeforms metasound graph, and you see I really work a lot with metasound patches. So if you dive into the whole thing, you see it's organized in metasound patches with a track setup here, and a lot of stuff going on there, and it's really quite a big monster here. But at the end of the day, it really works. So let's see. I'm hitting play here. It starts with the track. Updating the randomizers constantly. With new probability settings, and filters are changing. Everything works pretty much the same as in the original version. But as you see, I didn't even start the game. I just pressed play on this metasound here. And I've got a timer for a new track, a track change. I think it's 2 minutes, so we should be there pretty soon. Working with 2 decks here, like a DJ, toggling between 2 tracks. Or I can even trigger the new track a little bit early. Let's do that. Trigger the transition to a new track. New track is randomly being chosen. Here it comes. The crossfade and new parameters for the new track, new randomizer settings. And as you see, everything happens here inside of one big metasound, and no blueprint is involved here. So before we get into the details here, let's quickly talk about the differences of doing script logic in metasound compared to blueprint. And this is really very, very different. The documentation says that a blueprint is something they call an execution graph, and a metasound is something they call a flow graph or a DSP rendering graph. And first difference is a blueprint is completely event-based and event-dependent. So if you don't have an execution event in a blueprint, nothing is going to happen. Every node needs execute event to start it, to make it do something. And this is not true for a metasound. A metasound is an audio DSP graph which will, as soon as it's being started, produce an audio stream, render an audio stream, calculate an audio stream for each and every sample at sample frequency. So 48,000 times per second, there needs to be a new value for your audio stream, a new sample value. And this is happening whether you are placing some trigger events in there or not. So the trigger events are not essential for a metasound. Let me show you. If I have an empty metasound here, I can easily just put in, let's say, a sawtooth oscillator, and there is an audio output, and this will, at the very moment when I'm pressing play here or spawn that metasound in my gameplay, will start producing audio signal here. And after that, I could, for instance, add some more DSP processing, like a filter, and putting that to, let's say, I don't know, 3000 hertz, filter it off. And after that, I'm adding a little mixer here and lower the volume a little bit so it doesn't get too loud. And then I'm connecting that to the output. So there is no trigger event happening here. It's just a series of DSP nodes here, and at the moment I'm pressing play here, I'm immediately getting audio signal because it starts rendering 48,000 times per second. This graph will calculate the new value for the audio sample. And for all other nodes that are not producing audio signal but other data types like float values, integer values, string values, time values, Boolean values, stuff like that, more or less the same is true. They are also constantly being calculated and updated, but not at sampling frequency, not at 48,000 hertz, but at control rate, which is 100 times per second, 100 hertz. So if I'm using an LFO node here, the output here is updated 100 times per second because it's just a control signal and not an audio signal. But still, I don't need any trigger events here. I don't need any execute event that starts the whole thing. It will just work. The moment I'm hitting play here, it will produce a control signal. So if I'm connecting this, let's say, to the cutoff frequency, and then let's say oscillate between, I don't know, 400 hertz and 2000 hertz at the speed of 5 hertz is fine. It will immediately start to modulate the cutoff frequency of the filter without any trigger events. So that's one big difference between a flow graph and an event graph, because in an event graph, nothing's going to happen if you don't have that execute event. And another big difference is that in this event graph here, everything is happening as a sequence of events. If let's grab that variable here, an integer variable, and I'm reading out that value, and then let's increment it. So that's one first event that's going to happen. So that calculation is being done, and I can go and store that back into the same variable. And maybe let's do a print string here. And let's print that one to the screen. And after that, I can do some more calculation, like multiply it by 5 or whatever. And then we go and store it again. And we could do another print string and read it, oops, and read it from here. Complete chaos here in my in my graph, but you get the gist. So this is all happening in a sequence. So I can read out the variable, store it, do something with it, do another calculation, store it again, and read it out again, one after the other, as a sequence of events. This would never ever be possible in a flow graph, because in a flow graph everything is being calculated in one go as a part of one big equation. So if we don't need these trigger events for our flow graph to work and to produce audio, what are these triggers and what do we use them for? Well, basically I will just see them as timestamps. I can mark specific cycles of recalculation, specific samples in our audio rendering process, and do something with that timing information. For instance, if I'm using this on play input, trigger input here, which is always there, this just basically marks the very first cycle of audio calculation, the very first sample, and passes on that information to, for instance, a wave player node. Let's use a wave player node here. And if I'm connecting this trigger input to the play input of a wave player node, it just tells the wave player that it should start to do its thing at the very first sample, meaning at the very first round of audio calculation after this meta sound is being started. So let's just use, I don't know, there is this click on button sound, a very short sound, and put that one into here. 0.2 should not be too loud, which just says, okay, this wave player gets the timing information that at the very first sample it should start to produce audio. This trigger does not interfere with the timing of the audio rendering. This is constant, 48,000 times per second the calculation of the whole graph is being done, and the information, the timing information of this trigger is just part of one cycle of calculations here. So that's the reason why I could easily use the same trigger input twice in one graph here. So like if I want to reset the sync of the LFO, I can use the same input trigger because it just marks this exactly same sample as at the very first sample, go start the wave player, and also with the same timing information reset the LFO cycle. Let me add a repeat node here, a trigger repeat node here, just to give you one more example. If I'm inserting that here and let's set a timing period to 1 second, the only thing that happens now is that this trigger repeat node will start at the very first sample of calculations, and after 1 second, which means 48,000 samples later, there will be another timing information that will restart that wave player. And so we have So another way to see this is that triggers are just Boolean variables that are normally set to false, and for specific samples, for specific points in time in our audio rendering stream, they are set to true just for one sample, and on the very next sample they're back to false. So that's another way to see it. And for each sample that is being calculated, every variable, every value has to be defined before the calculation starts. And then everything can be calculated in one go, and then the calculation of the next sample is coming up. And that has several implications because, for instance, that I have a float variable, and if I'm holding shift and drag it to my graph, I get a setter node. And so that means I can set the value of my variable at a point in my graph, but I can only do that once. So I can connect it here. So everything is defined for my calculation, but it has to be clear before calculation starts if this variable has this one value or another value. So if I'm trying to hold shift again and place my variable as a setter at some other point in the graph, it just won't let me. It would just point out, hey, you already got a setter node, and one setter node is allowed in a flow graph and not more, which is pretty different from what we did here, because we set the value of my number variable here for the first time, and later on in the graph we set it for a second time, which is something that doesn't exist in a flow graph. There is no later on, because this is one equation that is done in one go. So variables can only be set once in a graph, and another implication of that is if another node is calculating the timing of another trigger event, like here in the wave player, and once the wave player knows which wave asset to play and when it should start playing, then it could calculate the timing of, let's say, for instance, the unfinished trigger. This is just another timing information, and it needs to be known before the calculation starts, and it can't be known because when the wave player starts with the play trigger event here, only then it will know when the unfinished event is going to happen. It can mark that sample in my audio stream. So this cannot be calculated in one go, and therefore it's not possible to do some kind of loop in my flow graph here. So let me give you a quick example. It could be an idea that you say, okay, let's not use one specific wave asset, but let's promote it to a graph variable and make that graph variable an array of wave assets. Okay, and then when we want to play that wave sample or the wave asset, we're going to get a get random node for wave asset arrays. Okay, and then we connect that to the wave asset input here, and let's say on play, so at the very first sample, the first wave asset should be picked and then passed on to the wave player, and the play trigger is also started at the very first sample. And let's just quickly add trigger any here, because it could be possible that I want to place some other trigger in here. Okay, and then we would have to throw some samples on that wave asset array. And it would work in an event graph that you would say, if my first sample has finished to play, so there is a trigger event here, let's connect that back to that get the next array item trigger. And this is not allowed, because this cannot be calculated in one go, because this information is just not there at the beginning of the calculation, and so it's not allowed. Something you could easily do in an event graph. So this is very important to really understand that these kind of limitations are there, and you have to find workarounds, or you have to change the way you think about the logic, because it's always calculated in one go. But there's a workaround for this, and what you could do actually is that you promote this timing information, and it's basically just, it's another data type. So you could store that trigger event here, also a difference to an event graph, and you could store that to a variable, which would then be called unfinished. And there's a cool thing that you can do is, if you're dragging that variable back on the graph and you see the pop-up window, there is with the Alt key, you get a get delayed. So there's this little icon here that shows you that it's a delayed getter node. And what this does is it gets the value of the previous round of calculation. So the timing information is already there because we stored it, and we cannot use it right away, but on the next cycle of calculations, we can use the information of the last sample that has been calculated. So we've got a delay of one sample, and the important thing is when we start doing the calculation for the whole graph for the next sample, this value is already there, it's already stored, and so everything is prepared for the calculation, and this one would work. And even more elegant, that's why they placed this on nearly finished output here, because this will report one sample before my wave asset has finished playing. So normally I would do the connection like this, because then there is not even a sample gap in between, because this reports one sample before the wave asset has finished and stores that, and on the very next round of calculation we are grabbing that timing information that is stored here, and then we can do the whole calculation in one go again. So that's basically what you always have to keep in mind when you're working with flow graphs. It's pretty different from blueprint scripting in terms of logic, and I know we spent a lot of time now to discuss this, but I think it's important, and it will be the base for everything we're going to discuss from now on. So that took longer than I thought. Even the color of my hoodie changed, the weather changed, the sun is shining, and we're already over 20 minutes in. So let's get to the MetaSound hacks and tricks. And the first one is quantized triggers, because triggers are sample accurate, but sometimes you don't want that. If you're working in a musical context, you want your triggers maybe quantized to musical events like quarter notes or whole bars. And this is what I'm doing here. So first of all, I'm using a trigger repeat to establish my musical timing, which just means it started by on play, so at the very first sample, and I'm receiving BPM information here, converting that information to timing info, and you see here I'm using whole bars for that, and so my trigger repeat will start putting out timing information for whole bars, for the beginning of whole bars, constantly feeding that into the next node. And what I'm doing here is I'm using a trigger control, which is basically just a gate for triggers, and it starts closed, as you see here. So normally it will just ignore the incoming triggers from the trigger repeat. But at the moment an external trigger is happening here, like the retrigger input here, it will open the gate and wait for the next trigger coming from the trigger repeat. And when that happens, this trigger is passed on to the rest of the graph. But at the same time, I'm storing that timing information, and I'm using that timing information to immediately close the gate. But it's not really right away or immediately, but because loops are not allowed and this would not work. But what I can do, it's the same thing as we did like in the last example. I'm using the delayed get. So this is being processed one sample after my trigger control let my trigger pass through. It stores the timing information, and on the very next sample it uses that information to close the gate. And so we're back to a closed gate, and the next trigger repeat outputs here will be ignored until the next retrigger input here opens the gate again for one sample, and one sample later closes it back again. So that's a pretty easy setup, but quite convenient if you want to quantize triggers to BPM values. So trick number 2 is a quick one: random bools with randomizer weighting, because the standard node for random bools does not feature randomizer weighting. It will just output true or false with a 50-50 chance, and this is not always what we want. Especially in Sonic Lifeforms, I'm using random bools with weightings a lot, and so I had to come up with a solution for that. So what we do is we are using a node for random get from a bool array, because this node does feature randomizer weighting. The only thing we have to do is set up an array of bools, which is exactly 2 array elements long, true and false, and this gives us the option of feeding it some randomizer weighting, and then we have a random bool with weightings. So that's an easy trick: random bools with weights. So the next one is for situations that I would solve in event graphs, pretty much like this, where I have to set the value of one and the same variable to different values depending on a certain condition. And this is very easy in an event graph. You have this branch node and set a condition, and if it's true, you're setting the variable to that value. If it's false, you're setting the variable to the other value. Cool, but this is not allowed in a flow graph because you are not allowed to set the same variable in one flow graph twice. Only at one position in the flow graph you can use that setter node. And so this solution is just not possible in a flow graph. But what you can do in a flow graph is that you can manipulate the value that is being fed into the set variable node here. And you can use the trigger route node for that. And it's fairly simple. You've got two trigger inputs and corresponding value inputs. And depending on which input is triggered, that corresponding value will be fed into the set variable node here. So depending on a condition, you can determine which value goes into here. And if you combine that with the trigger compare node, then you've got pretty much the same setup as in the event graph. You've got two separate trigger outputs, and these could trigger these two corresponding values here. And another thing you could do is that you could stack those trigger route nodes. So this value input here, value 1, gets its value from another trigger route node, which is also dependent on two different separate trigger inputs, and feeding this value or the value of 0 into that value. So you can combine these, and this will allow for more complex setups. So a pretty similar example would be my automatic crossfade in my Sonic Lifeforms system. And for that, I'm using this value node, which is pretty similar to the trigger route node, because you also got two input triggers and corresponding input values. You've got the set trigger, which corresponds to the target value, and the reset trigger, which corresponds to the initial value input. And what you can do with this value node here is you can combine it with an interp2 function. So when an input trigger arrives here at set, it will start that interpolation process over time from initial value to target value. And I used that for my auto crossfading. So my auto crossfade is started by a trigger sequence node. Where is it here? Which is basically a trigger toggle. Output 1 and output 0 are alternating. And these triggers are fed into my two trigger route nodes here, representing my two decks. So trigger output 0 of my trigger sequence goes into set 0 and set 0 of both trigger route nodes, and the same is true for set 1. So they're always triggering the same trigger inputs here, but the values are like from 0 to 1 on the upper trigger route node and from 1 to 0 at the lower one. And if any of those is triggered, then we're going to start that interpolation. But the initial value and the target value are taken from here, and depending on which deck is triggered, they will go from 1 to 0 or from 0 to 1 over time. And I can set the time with a default value of 10 seconds here, and this will just be fed into my two crossfade nodes, and that's about it. And after that, I'm just documenting that my crossfade is done, and this information is being used somewhere else to switch off the deck that is not audible anymore. So the next one is just some basic thoughts and tips on organizing a really big meta sound. And this one has really grown into a monster of a meta sound here. And the only way I can keep things organized here with many variables and inputs and nodes is by organizing everything that I can in meta sound patches. So if you take a look, this one here is my master meta sound source, and all these other objects here are meta sound patches that I'm using inside of that meta sound here. So I've got this master meta sound here, and then I've got another patch for my player decks, and my player decks consist of 2 layers of 8 layers of music, and this is another meta sound patch. And if I'm going into that, I'm using more patches that represent my single player decks, and my single player decks, they also have some more meta sound patches, for instance the filtering. And yeah, you see everything is pretty organized in MetaSound patches. And another thing I wanted to show you, because I have to deal with a lot of values and variables here, and to keep things organized, I try to organize as much as I can in arrays. And where is it? Here in the track setup, here everything I'm doing is output as an array of 8 values, and there is no such thing as an array selector in MetaSound, so you have to build one on your own, but it's actually pretty easy. So what you do is you are just concatenating all of those arrays to one big master array, and then you're building a subset of that corresponding to your index value. It's just a simple math thing where you taking the index, multiplying that by 8, using that as a start index, and as I know I always have 8 array entries, I'm just adding 7 to that, and that will be my end index, and then I've got my selected array as one single array here. Okay, some workflows and tricks I came across while working on my project, and I hope it was useful for some of you, and see you next time.